Good afternoon. This review is going to focus on how to write ionic and covalent formulas. I'm Miss Mixell, and I'm one of the chemistry teachers at Eagle Crest High School. Our essential question for today is, can we write a valid formula for both ionic and covalent substances? So to review, before we start writing formulas, you should already have written down on the periodic table you're using the ionic charge pattern, which is based on the number of valence electrons for each column. If we remember, group 1, or the first column of the periodic table, has a single valence electron, and so it always gives away that electron and forms a +1 charge. This is known as the ionic charge. Group 2, +2 charge. Group 13, +3 charge. And then we switch over to the nonmetals on the periodic table. They are to the right of our stair-step ladder. And the nonmetals, the behavior changes. Because of the high electronegativity, or ability to attract electrons, nonmetals, instead of giving away their electrons, gain electrons. And so we can see group 14, -4, group 15, -3, group 16, -2, and group 17, -1. And as discussed earlier, we don't have a charge for group 18 because the noble gases do not give away or accept electrons. They are inert. They're happy with their full outer electron shell. So ionic bonds form between metals and nonmetals. An ionic bond occurs when electrons are transferred from one atom to another due to large differences in electronegativity, metals giving away their electrons and nonmetals gaining those electrons. And an ionic bond must be electrically neutral. That means they form in ratios where the charges cancel or balance out. We can see this as an example with lithium sulfide. Lithium has a single valence electron. It likes to give away its electron and form a +1 charge. Sulfur has 6 valence electrons, so it needs 2 more to gain a full outer shell. So when lithium bonds with sulfur, it's not going to bond together in a 1-to-1 proportion. We'll need 2 lithium atoms, each giving away a single valence electron, to bond with 1 sulfur atom. The lithium atoms will form +1 charges, sulfur atom a -2 charge because it gained 2 electrons. And if we look, a plus and -2 balance out to form an electrically neutral compound. A covalent bond forms between nonmetals. Electrons are shared between the atoms due to a small difference in electronegativity. Since they have equal abilities to attract electrons, nobody can take that electron, and thus they must share them. Covalent bonds are easy to spot within formulas because the prefix in the name makes it easy to identify covalent molecules. So if you look at your blue references, we're going to use a flow chart to help us learn how to write formulas for both ionic and covalent substances correctly. Please make sure that you have your blue reference flow chart out in front of you, along with your periodic table as we do this. Pause it. And just a reminder, on the back of your periodic table, there's a chart with polyatomic ions. Poly means many. These are ions that contain one or more atom that is covalently bonded together. So we can see the chart that's on the very back side of your blue periodic table. We'll be referring to that a lot as we write formulas. We'll also be referring to the Roman numeral chart because Roman numerals are used to show the charge of transition metals. These are the metals in group 3 through group 12 that have variable charges. And since their behavior varies, we don't have ionic charges labeled for them like we do the other groups because they can have different charges. So the Roman numeral in the name will tell you what the charge is. A Roman numeral 2 would signify a +2 charge. So here's our first example. Let's write the formula for lithium phosphide. The very first thing we need to ask ourselves is lithium phosphide ionic or covalent? Well, if we examine the two elements, lithium is a metal and phosphorus is a nonmetal. So hopefully we deduced that it is an ionic compound because ionic compounds form between metals and nonmetals. Once we've determined it's ionic, our process is shown below. From the base name, determine the cation and anion. So the symbol for lithium, the cation, is Li, and the symbol for phosphorus, the anion, is P. Use the periodic table or polyatomic list to determine the charge of each ion. If we look at our periodic table, lithium is in group 1, which always forms a +1 charge. Phosphorus is in group 15, which always forms a -3 charge. Crisscross charges and write as subscripts to give the compound a neutral charge. So the crisscross method is a shortcut that allows us to determine the formula by taking the numbers here and crisscrossing them as subscripts on the formula so that we can see how they will proportionally combine. A formula is simply a ratio of atoms, and this is allowing us to see that ratio. So if we crisscross, the +1 charge on lithium becomes the 1 atom of phosphorus we need. The -3 charge on phosphorus becomes the 3 atoms of lithium we need. Notice the numbers go in, but the charges do not. A formula does not have charges in it. It's a ratio of atoms. So we can see that we're going to need 3 lithium atoms to combine with 1 phosphorus atom in this formula. We don't have to write 1 subscripts, so our final formula would be written as Li3P. I'm going to highlight another way in which we can think about this formula, which is to think about how they combine and balance charges. So the other way to consider it would be lithium always forms a +1 charge, phosphorus forms a -3 charge. To get charges to balance out, I'm going to need to add 2 more lithium atoms, each with a +1 charge, making a +3 charge overall, which will cancel out with a -3 charge. Again, a formula is a ratio of atoms, so I have 1, 2, 3 lithium atoms combining with 1 phosphorus atom. All right, let's try another problem. Write the formula for lithium sulfate. Your first question should be, is it ionic or covalent? Hopefully you answered ionic because lithium is a metal and sulfate is a polyatomic ion composed of nonmetals. From the base name, determine the cation and the anion. What's the correct symbols for lithium and sulfate? Hopefully you said lithium symbol is Li and sulfate is SO4. That ATE helps us signify that this is not sulfide or sulfur on the periodic table. IDE is the monatomic version, just plain old sulfur, the element. 8s signify it's sulfur combined with oxygen. It's our polyatomic ion. That list we can find on the back side of our periodic table. Use the periodic table or polyatomic ion list to determine the charge of each ion. What charge does lithium have? What charge does sulfate have? Hopefully you told me lithium has a +1 charge and sulfate is a -2 charge. All right, now we need to crisscross the charges and write them as subscripts to give the compound a neutral charge. If polyatomic, let's make sure that we put that subscript outside the parentheses as it will represent how many groups of sulfate we need. So we're going to take the +1 for lithium and put it outside the parentheses to show we need 1 group of sulfate. And the -2 is going to become the 2 subscript on the lithium atom to tell us we need 2 atoms of lithium. Thus, our final formula will be Li2SO4. Notice I can remove the parentheses and the 1 subscript because if I only have 1 group of sulfate, there's no reason to show parentheses with a 1 outside. Again, another way to look at this formula is to consider the charges and writing a balanced neutral formula. So lithium has a +1 charge, sulfate a -2. I would need 2 lithium atoms, giving me a +2 charge, to balance out the -2 charge of a single sulfate group. Again, a formula is a ratio of atoms, so two lithium atoms, Li2, will combine with a single sulfate group, SO4. All right, let's write the formula for iodine heptafluoride. Is it ionic or covalent? Hopefully you answered that it was covalent because iodine is a nonmetal, fluoride is a nonmetal, and that Greek prefix, the hepta, should have given away that we are using a covalent naming process. Since it's covalent, from the base name, we're going to use the prefixes to determine the number of each atom. Iodine does not have a prefix in front of it. No prefix is allowed when we have a single atom and it's on the first part of the formula. So we can infer that we have one iodine atom. Hepta is the prefix for 7, so we have 7 fluorine atoms. And covalent is super easy because we just deduced the formula. We have one iodine attached to 7 fluorines, IF7. All right, let's write the formula of aluminum oxide. Start with your initial question. Is it ionic or covalent? Hopefully you told me it was ionic because we have a metal combined with a nonmetal. So our next step will be to determine the symbols of each. Aluminum is Al, oxygen is O. All right, what are the charges? What is the ionic charge for aluminum and oxygen? Al has a +3 charge, oxygen has a -2 charge. And if we crisscross to get our formula, the +3 charge on aluminum is going to become a 3 subscript on oxygen. The -2 charge on oxygen will become a 2 subscript on aluminum. This formula tells us we need 2 aluminum atoms to combine with 3 oxygen atoms. Final formula of Al2O3. Again, another way to think about it is balancing charges. Since aluminum has a +3 charge and oxygen has a -2, we need a common denominator. And so the common denominator would be 6. If I have 2 aluminum atoms, that's going to form a +6 charge. 3 oxygen atoms will form a -6 charge. And I balance and cancel those out to get my formula. 2 aluminums, Al2O3. All right, let's write the formula for iron 2 oxide. Start by determining, is it ionic or covalent? Hopefully you told us it's ionic because it's a metal combined with a nonmetal. Iron's a metal and oxygen's a nonmetal. From the base name, what's the symbol for the cation and the anion, iron and oxide? Hopefully you told me iron has a symbol of Fe and oxygen is O. Now we'll need to determine the charge of each iron. Iron has a charge of +2 because the Roman numeral signals the charge on the transition metal. Roman numeral 2 tells us iron has a +2 charge in this circumstance. And oxygen always forms a -2 charge. Let's crisscross to get our formula. When we do so, we will get Fe2O2, but we must remember that ionic formulas need to be reduced to the lowest ratio of atoms. That shortcut of crisscrossing is going to create a misconception unless we remember to reduce. And so our final formula should not be a 2-to-2 ratio. It should be a 1-to-1 ratio, FeO. We can see that better if we consider the other way. If iron has a +2 and oxygen is a -2, those already cancel each other out. So for every 1 iron atom, we need a single oxygen atom to combine with it. Okay, write the formula for us of dicarbon hexahydride. Dicarbon hexahydride. Start by determining, is it ionic or covalent? Hopefully you told me it was covalent because carbon is a nonmetal and hydrogen, hydride, is also a nonmetal. Again, the Greek prefixes of di and hexa tells us we have a covalent naming process. From the base name, we're going to use the prefixes to determine the number of each atom. Di means that we have 2 carbon atoms. Hexa means we have 6 hydrogen atoms. And since we know we have 2 carbons and 6 hydrogens, we can simply write the formula, C2H6. All right, we have 2 problems left. Let's write the formula for titanium, Roman numeral IV, oxide. Let's start by, is this ionic or covalent? We should recognize that this is ionic because titanium is a metal and oxygen's a nonmetal. Roman numerals kind of give that away. Anytime we see Roman numerals in the name, we know we have a transition metal and thus an ionic formula. From the base name, we need to determine our cation and anion. Titanium symbol is Ti, oxide is oxygen, just O. And now we'll need to determine the ionic charges. What does this Roman numeral symbolize? What charge is capital I, capital V? If you check the backside of your periodic table, you should see that that signifies a +4 charge. Oxygen always has a -2 charge. When we crisscross, we're going to get Ti2O4, the charge from titanium dropping in as the subscript on oxygen, the charge from oxygen dropping in as the subscript on titanium, and we must remember to reduce this to the lowest ratio of atoms. A 2-to-4 ratio can be reduced to a 1-to-2 ratio. For every 1 titanium atom, we need 2 oxygen atoms. Again, another way to look at this is if titanium has a +4 charge, I'm going to need 2 oxygens, each with a -2 charge. Those will balance out to create our neutral formula of 1 titanium for every 2 oxygen atoms. Here's our last problem. Start by identifying, is it ionic or covalent? Hopefully you told me it was ionic because calcium's a metal and carbonate is a nonmetal. It's actually a group of nonmetals, a polyatomic ion. Since it's ionic, let's use the base name based on the cation and anion. Calcium has a symbol of Ca. Carbonate is parentheses CO3, 1 carbon combined with 3 oxygen atoms. We're going to keep it in parentheses because we can't change any part of this formula as we build the formula. All right, what is the ionic charge for calcium? What's the ionic charge for carbonate? Calcium has a +2 charge, and if we look at the back of our periodic table, we can see that carbonate also has a -2 charge. When we crisscross, those charges are going to drop in as subscripts on the opposite atom. Calcium's +2 becoming a subscript to show we need 2 groups of carbonate. Carbonate's -2 dropping in as a subscript to show we need 2 calcium atoms. But again, we must reduce to the lowest ratio of atoms or groups. So we don't really need 2 calcium atoms for every 2 carbonate groups. A 2-to-2 ratio can be reduced to a 1-to-1 ratio. For every 1 calcium atom, we need 1 carbonate group, CO3. Another way to look at this is to balance charges, and when we see a +2 and a -2, we should recognize they're already balanced, and we're going to come together in a 1-to-1 ratio, CaCO3. I hope this was helpful. Have a great day.